Okay, today I'm going to talk about temperature and absolute zero. So temperature, as we think of it, is really a measure of the average kinetic energy, or another way of saying that is the average speed of the particles in a substance. All particles within the substance are not moving at the same speed. So in the end, the temperature is telling us about the average. If we were to really look at the particles within a substance, the speed that they're moving at would look a little bit like this. This is like a number of particles, and you'll notice I'm not putting any numbers on this graph because I don't know how many particles we have total. It's just a basic idea. And the speed of those particles always follows this sort of shape like this. It's kind of like a bell curve, but it stretches out on one end. This is called a Maxwell-Boltzmann distribution. And it tells you in a substance how fast the particles are going based on the number of those particles. So this speed right here would be the speed that is most likely for a particle. Or you could say that as the speed that most of the particles are traveling at. And then as you get further away from that speed, you can see you have less particles traveling at these faster speeds. So there's always some particles that are almost stopped down here that are going very slowly. If this is 0, sorry, I used V for speed because that's what we do in physics. Let me just change that to speed. You have some particles that are going at almost 0 meters per second, and then you go up to the most likely, where particles might be traveling around at whatever this speed is, and then at higher and higher speeds you have less and less particles until effectively you get down to the maximum speed of the particles at very high speeds, or the maximum speed of the particles, and there's very few particles up traveling on those very fast speeds. So here we can see we have more particles at this speed and less particles at this speed. And temperature tells us exactly what this shape is going to look like. I'm going to use a couple different colors here to try and make this point. So let's say red. We'll use red for the hot particles. Actually, let's make my graph first. So what does it really mean to be hotter? Well, a hotter distribution means this whole shape shifts to the right a little bit. What does it mean to be colder then? To be colder, it means that this whole shape shifts to the right a little bit. And then if we consider this our normal temperature, right down the middle, you can see that we can see what changing temperature really means. So this would be our hot, where all of the particles are going at a faster, they've been shifted this way, speed, a faster speed. Blue represents our cold. It's been shifted to the left a little bit, which means in general our particles have been shifted this way or have less speed. So hotter has more faster particles, colder has more slower particles, and temperature itself predicts the average of all the particles participating in this graph. So when we say that the temperature of a substance has increased, that doesn't mean that some specific gas molecule is necessarily going faster. What it means is if we consider all the gas molecules in the substance, they are in general going faster than they were when it was colder. Or if we say that it's colder, they are generally going slower than they were when it was hotter. If we think about this then, there's one interesting conclusion about this, and that is that if the particles are moving and that's what's creating temperature, then there should be some temperature at which the particles all stop. So there must be some temperature where instead of having this distribution, we would have all of the particles right here with a 0 speed, or when the particles stop. What this means then is that there couldn't be any colder than this. There's no way to go slower than being stopped. And so this would represent the absolute zero, or the minimum temperature that there is. The guy that did the work on this name was Kelvin, and he came up with this temperature. This is approximate, but at negative 273 degrees Celsius, which means then that minus 273 degrees Celsius represents when the particles stop, or it is the real minimum temperature that can ever exist. Kelvin said, well, if there's a minimum, why don't we make that temperature into zero, and then we won't have any negative temperatures at all. So he said, let's take our temperature of minus 273 degrees Celsius, and let's reset it in the Kelvin scale as 0 degrees, and then every temperature we have will be a positive number above that. So that means that our temperature in Kelvin wanted to take negative 273 and make it 0, so it took our temperature in Celsius and it added 273 degrees to it. When Kelvin made the scale, he kept the size of 1 degree the same. So there's no factor here. We don't have to multiply the temperature in Celsius by anything to make this conversion. All we have to do is add 273 degrees to it, and we get an absolute temperature that has no negative numbers in it. In subsequent videos, we're going to be doing some gas law calculations that deal with ratios. And when dealing with ratios, we always have to use absolute temperature. So it's important that we convert all of our temperatures to Kelvin if we're doing any sort of ratios with temperature. And that way we don't have to deal with any negative numbers. We get 0 really to be the absolute 0, the point where the particles stop. Again, this is called the Kelvin scale of temperature. So if we had, say, 25 degrees Celsius, and we wanted it in Kelvin, we wanted the temperature in Kelvin, we would just take our temperature in Celsius and add 273 degrees to it. So 25 degrees plus 273 degrees would give us 298 degrees. But instead of calling this Celsius, we would call this Kelvin, as that's the guy that made up this scale. One more quick example, let's just say our temperature in Celsius was minus 10 degrees C. To get our temperature in Kelvin, we would go our temperature in Celsius plus 273. So minus 10 plus 273. And we would get 263 degrees Kelvin. And you can see this is a useful scale because it doesn't have zeros. I guess quickly, just to be complete here, what if we had a temperature in Kelvin of, say, 300 degrees Kelvin? What would that work out to be in Celsius? So our temperature in Kelvin is equal to our temperature in Celsius plus 273. So 300 degrees is equal to the temperature in Celsius plus 273. And so if I move this over, it becomes minus 273. And so that would work out to be 27 degrees Celsius. So it's a bit complicated, maybe a little bit beyond grade 11, which is what this video is for, but that's really what temperature means. It means that there's a distribution of particles at different speeds, and some speeds are more likely than other speeds. To be hotter means you have a greater number of your particles at the faster speeds. To be colder means you have a greater number of particles at your lower speeds. And if temperature means speed, there must be some temperature that we associate with stopping. That temperature happens to be minus 273 degrees. And so Kelvin said, well, let's reset the scale so that 273 degrees is really 0, and so then we don't have to have any negative numbers in our temperature. This is important for doing ratios, and so we will always have to convert to Kelvin before we can use our gas laws.